All right, so today we are doing a deep dive with Butler Lampson and his paper, Hints and Princetons for Computer System Design.
Really diving into system design.
Yeah, this is like getting a master class from a legend,
For sure, a legend.
He's got a Turing Award. Was it Xerox PRC?
Yeah, he was there when a lot of this stuff we take for granted was being invented.
Yeah, exactly.
Yeah.
So in this paper, one of the things he does is lays out these like oppositions, right? These opposing forces in system design, like choosing between simple versus something that's more feature rich,
Right.
He doesn't necessarily say like, do this, not that. He's kind of pushing you to explore that whole spectrum.
Yeah,
right?
to understand the trade-offs.
Understand the trade-offs. And I think that's one of the things that's so brilliant about this paper.
Yeah, because making that decision for convenience now can be a huge headache in the future.
That's right. And it's something you really have to think about at the beginning.
For sure.
So he dives right in talking about the importance of simplicity. This idea of, keeping it simple, stupid.
The KISS principle, right?
Yeah, the KISS principle, exactly.
Yeah.
And, I think we've all seen what happens when things get overly complicated.
Oh, yeah, for sure.
But there's a hidden cost to that.
Yeah, and I think it impacts everything down the line. It's not just about making your own life easier, right?
Right.
There's a great quote about that by John Carmack, the game developer. He said that, the cost of a feature isn't just the time it takes to code it, it's how much harder it makes every future change.
Oh, wow.
Yeah, and that ripple effect just grows and grows.
That's so true. It's like you add a feature here, you add a tweak there,
Yeah.
and all of a sudden it's like, how did we get here?
Totally.
And it's just this tangled mess. And I think about some of the software we use every day, like word processors or web browsers.
Right.
I mean, those things are packed with features.
Yeah, but behind the scenes, oh man.
Oh, it's a nightmare.
It can be a nightmare.
So he's not saying no to features.
Right.
He introduces this idea of components as a way to strike a balance.
Yeah.
And this is interesting. It's sort of these modular building blocks, right?
Right.
Where each one is simple on its own, but you can combine them in these endless ways, right?
Yeah. You can create really powerful and complex systems, but using simple pieces.
Okay, so like building blocks of complexity. I like that.
Yeah.
What kind of real-world examples are we talking about when we talk about components?
Well, I mean, there's tons, but one that comes to mind is a key value store. And it's a very simple concept. At its core, you're storing data as key value pairs, like a dictionary. But it's so simple that it's so versatile.
Right.
And that forms the backbone of all sorts of systems, from databases to distributed caches.
So you're saying that by keeping the individual components simple and well-defined,
Yeah.
you kind of create this system that's both really powerful but also manageable?
Exactly.
It's really profound when you think about it.
It is, and you can use it for so many things beyond just software.
Okay, so embrace simplicity, build with components.
Yeah.
Got it. But then Lampson throws us a little bit of a curveball.
He does.
He says perfection is overrated.
Yeah, but he's not telling us to settle for mediocrity.
No.
Right. It's not about that at all.
He's not saying just do a half-a job.
Yeah, exactly. This is Butler Lampson we're talking about.
Right, exactly.
But it's about understanding that in system design, this pursuit of absolute perfection, it can actually be counterproductive.
Okay.
So he talks about striving for good enough and designing systems that have what he calls flaky, springy parts.
Flaky, springy parts.
Yeah, so these are components that, they might not be perfect, but they're resilient and they can handle those unexpected situations.
Okay, help me wrap my head around this. What would be an example of aiming for good enough in system design?
So think about system uptime.
Okay.
That holy grail of 100% availability. Now, achieving that is incredibly difficult and expensive, maybe even impossible for a lot of systems. But what if, instead of aiming for that perfect uptime, you aim for 99.5% uptime?
Okay.
You're still talking about an extremely reliable system.
Extremely reliable, yeah.
But by accepting that tiny bit of imperfection, it gives you flexibility and opens up opportunities to make other improvements to the system.
So it's about finding that sweet spot where it's reliable enough for the vast majority of cases, but you're not getting bogged down in those complexities of chasing those last, percentage points of perfection.
Yeah, and this comes up in all sorts of things from, like response times with probabilities, cache hit rates, even something as, seemingly trivial as hyphenating words in a document.
Okay.
Sometimes aiming for perfectly hyphenated text can lead to overly complex algorithms and slow down the entire system.
Wow. So it's like giving yourself permission to not sweat the small stuff.
Yeah.
As long as the overall system is functional and reliable.
As long as it works, right?
Right, yeah.
And you can always go back and improve it later.
It's a very different way of thinking, for sure.
It is.
So how does this good enough philosophy translate to, say, our everyday lives?
That's a great question. I think it's about recognizing that, life itself is inherently imperfect, right?
This is true. This is true.
And sometimes striving for that absolute perfection can actually hold us back.
Okay.
Maybe it's accepting that your house will never be perfectly clean, or you won't always have time to cook a gourmet meal,
Yeah. No, you're telling me my to-do list is never ending.
Right.
And that's okay.
Exactly.
I'm learning to embrace good enough more and more each day.
There you go.
But before we all get too comfortable with imperfection,
Yeah.
what's the next principle that Lampson wants us to explore?
Well, next up is a big one. The power of immutability.
Immutability.
Yes.
Okay, and this is where things get really interesting.
This is a good one.
So this is about designing systems with data that, once created, cannot be changed.
Exactly.
Okay, that sounds intriguing, but also a bit restrictive.
It does.
Why would you want data that you can't change?
That's what I thought, too, when I first heard about it.
Yeah.
Like, what's the point, right?
Right.
Why even bother? Yeah, it seems kind of counterintuitive at first.
It does.
But think about it this way. When you have data that's constantly changing, you're always playing catch-up, right?
Yeah.
You have to worry about keeping track of all those changes, making sure everyone has the latest information, dealing with conflicts if multiple parts of the system are trying to change things at the same time.
Oh, yeah.
It's a mess.
It's like trying to solve a jigsaw puzzle where the pieces keep moving around.
Exactly. That's a great way to put it.
Yeah.
And especially in these really massive, complex systems, right?
Yeah.
Where you have tons of moving parts.
It'd be impossible.
It can be really, really tough.
Yeah.
But with immutable data, you eliminate that whole layer of complexity.
Okay.
Once a piece of data is created, it's like it's frozen in time,
Right.
It's never going to change out from under you.
So it's about creating this sense of predictability
Yes.
and stability
Yes, exactly.
in a world that's inherently unpredictable.
Which is everything in the computing world.
Yeah, exactly.
Especially in concurrent systems
Right.
where you have multiple processes happening at the same time.
Oh, yeah.
If you can guarantee that the data isn't changing,
Yeah.
you can avoid all those nasty concurrency bugs, race conditions, deadlocks, all that stuff.
It's like you're taking a variable, and in programming, you just make it a constant.
Exactly.
And there are actually some programming languages where you can do that, right?
Yeah, there are.
You could say, like, this is it. It could never change.
That's it. This is the value. It's done.
Yeah, and so it sounds like this could be, a real lifesaver when it comes to building those, bulletproof, reliable systems.
For sure.
That everyone seems to want these days.
Yes, reliability is key.
Yeah, but I have to imagine there's got to be some downsides to this approach, right?
Of course, there are always trade-offs, right? Nothing's ever perfect.
Right.
And in this case, the biggest challenge with immutability is that if you want to change something,
Yeah.
you technically have to create a whole new copy of the data with the modification.
Okay.
And for large data sets, that can be really expensive in terms of storage space.
So it's a trade-off between simplicity and storage.
Often, yeah.
You're essentially trading disk space for this more predictable, more manageable system.
That's the basic idea.
Okay, so how do you deal with that?
Well, luckily, Lampson, he's brilliant, and he doesn't just point out the problem.
Right.
He offers solutions. So
Okay.
one way to deal with this storage overhead of immutable data is to use something called MVCC.
MVCC.
Yes, it stands for Multiple Version Concurrency Control.
Multiple version concurrency control.
Yes, and it's very cool.
Okay.
It sounds complicated,
It does.
but it's actually quite elegant.
Yep.
So instead of directly overwriting data when you make a chain,
Right.
MVCC systems, they keep a history of all the different versions of the data.
Oh, okay.
So when you update something, you're essentially creating a new version and leaving the original intact.
So you always have this record
Right.
of how the data has changed over time.
You got it.
It's almost like version control for your data.
Exactly, like Git, but for your data.
Yeah.
And it's super powerful because it gives you the best of both worlds.
Okay.
You get that simplicity and reliability of immutability, but without the massive storage costs
Gotcha.
that come with constantly copying the entire data set.
Okay, that's seriously clever, MVCC. I'm adding that to my list of things to learn more about.
Yes. It's a good one.
What about, are there other ways to handle this trade-off?
Yeah, so he also talks about using specialized data structures that are designed specifically for immutable data.
Okay.
Things like append-only logs, where
Mhm.
new data is always added at the end of the log, and these things called boo trees, which are optimized for storing data in a tree-like structure that minimizes the amount of copying that's needed.
So these are like purpose-built tools?
For dealing with the unique challenges of immutable data.
For sure. And the really cool thing is that these aren't just theoretical concepts.
Yeah.
They're used in all sorts of real-world systems
Oh,
today.
cool. Okay, like what?
Well, for example, there's this thing called Immutable.js,
Yeah.
which brings the power of immutability to JavaScript.
Okay.
And then you have log-structured file systems and databases that leverage these ideas to make systems more robust and easier to reason about.
So it's not just some abstract computer science-y concept.
No.
It has like real implications for how we like build and interact with technology every day.
Absolutely.
I'm starting to see why Lampson dedicated a whole section to this.
Oh, yeah, it's a very important concept, and it
Yeah.
kind of speaks to that broader theme of
Yeah,
carefully considering the trade-offs in system design.
for sure.
Sometimes a slight shift in perspective, like embracing immutability,
Okay.
can unlock this whole new level of robustness and scalability.
That's a great point.
Yeah,
That's about challenging our assumptions
for sure.
and considering different approaches.
Exactly.
Now, speaking of different approaches,
Yes,
I know Lampson tackles another big one in his paper,
he does.
the age-old battle between
Classic stuff.
centralized and distributed systems.
That's right. Yes, the eternal dilemma.
Right.
And Lampson does not shy away from the complexity of this one.
No, he doesn't.
He actually starts off with this great quote from another legend, Leslie Lamport,
Okay.
who famously said that, and I quote, "A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable."
Oh, that's great.
Isn't it?
And terrifyingly true.
It is terrifyingly true.
I've definitely been bitten by those unknown unknowns
Oh, yeah, we all have.
before. But seriously, like, why do we even bother with distributed systems
Right.
if they can be so complex
Yes.
and prone to these weird, unpredictable failures?
Yeah, that's the million-dollar question, isn't it? And the answer, of course, is in the incredible advantages that distributed systems offer,
Okay.
especially in today's world.
Right.
For one thing, they can be so fault-tolerant because you've spread the workload across multiple machines.
Yeah.
So if one part of the system crashes,
Right.
the rest can often keep humming along.
It's like that old saying, don't put all your eggs in one basket.
Exactly.
With distributed systems, you're spreading the risk.
Exactly. And it makes them really well suited for those applications where downtime is simply not an option.
Right. Right.
Think e-commerce, finance, healthcare,
Yeah.
those mission-critical systems.
Okay, so resilience is a major plus. What else we got?
Well, the other big one is scalability.
Okay.
If you need more power, more capacity, you simply add more machines to the system.
Right.
With a well-designed distributed system, you can theoretically scale almost infinitely
Wow.
to handle those massive amounts of data and traffic, and that's just not possible with a centralized system. Sure, you're limited by the capabilities of that single machine.
Yeah, it's like the difference between a one-man shop and a global corporation.
Exactly. Exactly.
I have to admit, though, the thought of, like, managing a large distributed system
Oh, yeah.
makes my head spin a little bit.
It's a lot.
How do you keep track of all those moving parts and make
Yeah.
sure everything's playing nicely together?
Well, it's definitely a challenge, but that's where, good design principles
Right.
and the right tools come into play.
Right.
And Lampson talks about the importance of separating what he calls the control plane from the data plane in distributed systems.
Okay, those sound like very important sounding terms.
They are.
Break those down for me.
Absolutely. So think of it this way.
Okay.
The data plane, that's where the actual work of processing and storing data happens.
Okay.
It's like the factory floor, right?
Okay.
Where all the action is.
All right, so I'm visualizing conveyor belts,
Yes.
busy robots.
Exactly.
So where's the control plane?
So the control plane is what's managing and orchestrating all that activity on the factory floor.
Okay.
It's responsible for things like configuration, monitoring, coordinating how the different parts of the system work together.
So if the data plane is the factory floor,
Yeah,
The control plane is like the management team making sure everything runs smoothly.
exactly.
Okay.
And this separation of concerns is crucial in distributed systems
Ah.
because it allows you to manage that complexity more effectively,
Okay.
right? So you can think about something like Kubernetes,
Okay.
which is used to manage these containerized applications.
Right.
Kubernetes itself would be considered part of the control plane
Okay.
because it's responsible for deploying and managing those containers, whereas the applications running inside the containers,
Right.
which are handling the actual data, that would be part of the data plane.
Okay, so it's not just about choosing between centralized and distributed.
Right.
It's about understanding the trade-offs, designing systems that can handle the unique complexities of distribution.
Yeah. Yeah. And this separation of control and data seems to be key to making those systems manageable at scale.
It seems like it, yeah, and it kind of leads into this next opposition that Lampson talks about, this idea of fixed versus evolving.
Yes.
And this one's all about designing systems that can adapt to change, which, I mean,
Hugely important.
hugely important these days, right?
Especially in our fast-paced, ever-evolving technological landscape, it's more important than ever.
I mean, it's funny how that traditional, like, waterfall model of software development,
Right.
where you plan everything out in advance
Right.
and you try to stick to that plan no matter what.
The blueprint. Yeah.
It just falls apart in the real world.
It does.
Things change, requirements evolve, new technologies pop up. It's like trying to hit a moving target.
It's impossible.
Yeah.
Yeah, and that's why Lampson is advocating for these more iterative and agile approaches to development.
Okay.
So instead of trying to create that perfect system up front, you're embracing change by building in flexibility and adaptability from the very beginning.
So instead of one massive launch,
Right.
it's more about making incremental progress,
Yes.
testing, learning, refining along the way.
Exactly.
And key to this whole idea of building systems that can evolve
Yes.
is this idea of modularity and extensibility.
Yes. Love it.
Okay, I feel like this is another one of those two closely related but distinct concepts kind of moments here.
They are, but they're both important, right?
They are, yeah. Yeah. So modularity, that seems pretty self-explanatory to me. Break things down into smaller chunks.
Yeah, create those self-contained units, like
Yeah.
building blocks that can be developed and maintained independently.
Right. Okay, so where does extensibility come in?
So extensibility is taking that idea a step further and thinking about the future.
Okay.
It's about designing those modules with these clear interfaces and hooks so you can add new functionality later on without having to rewrite the whole thing. It's like, if you're planning an extension to your house,
Yeah.
you don't want to have to rewire the entire place just to add a new outlet, right?
I love that. That's a great analogy. It's like future-proofing your code,
Exactly.
building in those expansion slots right from the start.
I love that. I'm going to use that.
That's a good one.
It's such an elegant way to think about it,
It is. It is.
Designing systems that can grow and adapt over time.
And you see this principle in action everywhere, right?
Yeah, for sure.
Think about HTML.
Okay.
They can introduce new tags, new features, without breaking all the websites that were built years ago.
Right.
Or operating systems with device drivers.
Right.
You can plug in a brand new printer
Right.
without needing to modify the core OS code.
That's amazing when you think about it.
It is extensibility in action.
It's like the difference between a rigid structure and like a living, breathing organism that can adapt to its environment.
I love that. That's a great way to put it. So to sum up, if we want to build systems for the long haul,
Yes.
we've got to ditch the waterfall, embrace change, design with modularity and extensibility in mind.
Couldn't have said it better myself.
All right, so this focus on building for change
Yes.
leads us nicely into Lampson's next insight,
Okay.
this distinction between policy and mechanism.
Oh, this is a good one.
This sounds intriguing. I have a feeling I'm going to need a little help unpacking this one.
Of course. Happy to help. So think of it this way.
Okay.
The mechanism is the how of a system, right?
Okay.
It's the underlying code, the nuts and bolts that determine what the system can do.
Right.
The policy, on the other hand, is the what.
Okay.
It's the set of rules or guidelines that dictate how the system should behave.
Okay.
And importantly, those policies, they often need to change over time, right?
Right.
Even if the underlying mechanisms stay relatively stable.
So give me a real-world example. How does this play out in, like, in a way that someone like me who doesn't spend all day, thinking about code can relate to?
Okay, so let's take the example of security.
Okay.
A system might have various security mechanisms built in, like access control lists,
Right.
that determine who can access what data.
Sure.
But the actual policy, who should have access to what,
Yeah.
That's something that often needs to change based on the evolving needs of the organization.
Right. So the system itself provides like the tool,
Or mechanisms.
the mechanisms for managing security.
Right.
But it's up to the humans, the policymakers, to decide how those tools are actually used.
Exactly.
And those policies can and should change over time as circumstances change.
100%.
It's about having that flexibility.
Flexibility is key, and it applies to all sorts of areas beyond security, too.
Well, for sure. Yeah.
Think about resource allocation in a company. The system might have a mechanism for dividing up resources among different teams.
Okay.
But the policy, how much each team gets and for what purpose.
Right.
Those are decisions that likely need to be revisited and adjusted regularly as the company grows.
For sure.
And priorities shift.
Yeah. This is making me realize how many like invisible policies are kind of baked into the systems that we use every day.
Oh, yeah.
From like the algorithms that decide what we see on social media
Yes.
to the rules that govern, financial transactions.
Totally.
It's like this whole hidden layer of decision-making.
It is a hidden layer.
Wow.
And that's why Lampson's emphasis on separating policy from mechanism is so important.
Right.
It's about designing systems where those policies can be easily understood, evaluated, and modified as needed without requiring this complete overhaul of the entire underlying system.
So it's about building systems that can adapt.
Yes.
To the ever-changing landscape of human needs and priorities.
100%. That's a great way to put it.
Okay, so we've covered a ton of ground here, from embracing simplicity and imperfection to designing for adaptability.
Yep.
And separating policy from mechanism.
Big concepts.
But Lampson, being the master of system design that he is, leaves us with one final.
It does.
And surprisingly timeless trade-off. Time versus space.
A classic dilemma.
And in the world of computing, this trade-off takes on some pretty fascinating dimensions.
It does.
But often it boils down to this.
Yeah.
You could use more storage space to get faster results.
Often, yeah.
That feels very relatable, even in my non-technical life.
Right.
My apartment is a testament to that principle. Why organize and create space when you can just buy another shelf?
Exactly.
But how does this play out in the world of system design?
Well, so let's take the example of database indexes.
Okay.
An index is essentially a copy of some of the data in the database that's organized in a way that makes searching much faster.
Okay.
So by using more storage space for that index,
Yeah.
you gain a significant speed advantage when it comes to actually retrieving that data.
Yeah. So it's like having a detailed table of contents.
Yes.
For a massive book.
Exactly.
Sure, it takes up a few extra pages, but
Yeah.
it saves you tons of time when you need to find a specific piece of information.
Exactly. And this same principle applies to all sorts of things, from caching frequently accessed data in memory
Right.
to pre-computing these complex calculations and storing the results.
Sure.
It's all about strategically trading off storage space for speed and efficiency.
Right. So it's a balancing act.
It always is.
Sometimes it makes sense to splurge on the storage to save the time, and sometimes it's better to be more frugal with your bytes, even if it means things run a little bit slower.
It depends on the situation, right?
Right, exactly.
And what's even more interesting is that sometimes saving space can also lead to faster results.
Wait, really?
Yeah.
How does that work?
Well, think about data locality.
Oh.
If you can store data closer to where it's needed,
Yeah.
like caching files on a user's computer instead of making them go all the way back to a remote server, you can often reduce the time it takes to access that data, even if you're not necessarily using less storage overall.
It's like the difference between walking to your bookshelf to grab a book
Yes,
versus like having to drive to the library.
perfect analogy.
So it all comes down to understanding the specific constraints of the problem you're trying to solve.
Yes,
And finding that right balance
in the right balance.
between these competing factors of time, space, and efficiency.
Exactly.
Wow, this has been an incredibly insightful deep dive.
It has.
Butler Lampson's paper is it's packed with so much wisdom about how to design systems that are not just functional,
Right.
but elegant, adaptable, and resilient.
Couldn't agree more.
And what I appreciate so much is that he doesn't present these concepts in like this dry, theoretical way.
No, he doesn't.
It's like it's grounded in these real-world examples and humorous anecdotes and these thought-provoking quotes
He's got great quotes in there.
from other luminaries in the field. It's really like having a conversation
It is.
with a brilliant mentor who's seen it all
He has seen it all.
and is eager to share, his hard-won insights with the next generation
100%.
of builders and creators.
Yeah, it's a great paper.
And one final thought from Lampson that I found really interesting
Okay.
was this idea that for long-term data persistence,
Yeah.
sometimes the simplest methods are the most reliable,
Interesting.
which seems kind of counterintuitive,
Well,
right?
it does.
You would think in this age of fancy databases and cloud storage and everything else,
Yeah, you'd think we'd be beyond that.
we would have moved beyond plain text files.
Right.
But his point is that these simpler methods,
Yes,
they've stood the test of time
they have.
because they're inherently more robust
Delay. Yeah.
and less susceptible to corruption or obsolescence.
Makes sense.
I mean,
Yeah.
think about it. A plain text file
Yeah,
can be opened and read by virtually any computer system,
it's true.
regardless of what software or operating system is running.
Yep, it's universal.
And relational databases, while more complex than text files,
Sure.
they still rely on this relatively simple and well-understood model
Right.
for storing and organizing data.
They're not going anywhere.
So sometimes the best solutions are the ones that have been staring us in the face all along.
Often, yes.
It's a good reminder that innovation doesn't always have to be about reinventing the wheel,
Totally.
but about understanding the enduring power of these simple, elegant solutions.
100%. That's a great way to put it.
And with that, I think we've successfully navigated the intricate landscape of Butler Lampson's hints and principles for computer system design.
We made it.
This has been an incredible journey.
It has.
I feel like I've come away with this whole toolbox of new concepts and principles to apply to my own work, to my own life even.
Love it.
What about you? What resonated most with you from our deep dive into Lampson's work?
I always come back to his emphasis on simplicity and clarity of thought, It's just a powerful reminder that even in the face of immense complexity,
Right.
most elegant solutions, they often start with that deep understanding of the fundamentals.
They do. That's a great takeaway.
It is.
And on that note, we want to hear from you, our listeners.
Yes.
What insights did you glean from this deep dive?
What resonated with you?
What are you going to do differently in your own work, in your own life, because of what you learned today?
We want to know.
Head over to our social media channels.
Yes, join the conversation.
Join the conversation. We can't wait to hear your thoughts.
Until next time, keep exploring, keep questioning, and keep diving deep.
Nicely done.